So, as I promised, we're going to do a titration calculation together, and this is it. The way I can tell that something is a titration, there's a few clues. The first thing is I'm reacting an acid with a base. So here we have sulfuric acid and sodium hydroxide, so acid and a base. The other way I can tell is the precision is very high. All of our burette measurements are going to have 2 decimal places of precision, and usually we use the base in the burette. And all of our pipette measurements will also have 2 decimal places of precision. So when we do a titration, our goal is to figure out the concentration of something. We usually know the identity, like in this case, we know sulfuric acid and we know sodium hydroxide, but we don't know the concentration of the unknown. Okay? So when I read these problems, I'm still looking for where we have numbers with units, highlighting that. It's also important to know what chemical we're talking about for each of them. You'll notice that keyword of is here again. So that's what we're going to use to get us started. So we have 1.0. I'm actually going to move this up. We're going to need some space. So we have 1.0 molar. I'm going to turn that into moles per liter of NaOH. It is critical to write the chemical and the unit of measurement, otherwise you're going to get lost. And it says that 24.05 milliliters of that were used. So of still means multiplication. Now I know that liters and milliliters don't cancel, so I'm going to do an additional conversion here. So that now we'll be in terms of moles of NaOH. The question is asking us to figure out how many moles of acid are present. So I'm going to have to use a molar ratio. So I want to cancel NaOH. We have 2 moles of NaOH here. And I'm going to get it into how much acid we have, which is H2SO4. So this step cancels NaOH, and now we have moles of sulfuric. When it comes to actually doing these problems, remember everything on top gets multiplied together and everything on the bottom gets divided. So I'm entering 1 times 24.05, right, which is of course 2405. You don't even need to enter the 1. Then that divided by 1,000, and then that number divided by 2. And so we get our final answer is, the calculator says 0.012025, and that would be moles of H2SO4. Now, because this question specifies that they want to know moles, I have to look back at my significant figures, okay? And in this particular problem, it looks like we only have 2 because we don't know very well what the concentration of our NaOH is. So if that's the case, then I have to round to 2 sig figs. These are not significant because, of course, it doesn't make sense to say we have 0 concentration. So we'll keep the 1 and we'll keep the 2. Okay, so that's answer to the first part of the question. Most titration questions are actually interested in what the concentration of the unknown acid is. So in this case, in order to get to concentration, which is molarity, we'll first convert the milliliters into liters. Keep your sig figs again, so it's going to be 3 zeros at the end. That's liters. And I'm going to keep extra sig figs. I'm not going to use the rounded value here. I'll keep what's in my calculator. So what I'm actually going to enter is that the molarity equals all the moles divided by the correct number of sig figs. I'm just going to note this is my, however you want to, this is your last significant digit. All right. Really what I put in the calculator is divided by 0.01. And we get 1.2025. If I round that to my 2 sig figs, it'll just be 1.2. My unit is molarity, and the chemical there is H2SO4. Now, I want to talk a little bit about the lab, how you are going to structure that says H2SO4 in the captions. Sulfuric acid. Okay, it's not cooperating. I hope you know that sulfuric is H2SO4. Anyway, I want to talk a little bit about how you're going to organize your information for lab. So when you do titration, the first thing you want to have is you need to have an initial burette reading. In our case, our burette will contain the NaOH. And then you'll have a column for the final burette reading. These are all, by the way, these are milliliters. I should put that at the top. The other information that you'll have to record is the mass of the oxalic acid that you're going to weigh there we go. That you're going to weigh out and put into a 250 ml volumetric flask. So that's going to also have a lot of significant digits because it's a volumetric piece of glassware. I'm going to move my picture to the other side so I'm out of my own way. All right, so let's just pretend you guys are going to do your own measurements. You're going to have a pre-lab that helps you figure out what your minimum amount of oxalic acid is and what your maximum amount is, and you're going to weigh out in between there. You need to record the exact mass, all right? And so when I say exact, I'm actually wrong. You can't record an exact mass, but you can record a precise mass, okay? So you're going to use the balances in the instrument room to do that. Make sure you watch the video about how to do that. They're different. They're not the ones on your bench. And so basically you will take some mass, all right? Let's just say I measured exactly, again, it's not exact. I keep saying that word because we use it in regular language and it's not. Measurements are never exact. But I will measure precisely 3.0000 grams. Okay, that's a valid amount. Yours will vary. Remember that it's oxalic acid dihydrate when you measure it. Okay, and then let's say I start my burette at exactly 0. Oh my gosh, I keep saying exactly. I have to stop that. Horrible habit. But I will start it at precisely 0.00 milliliters. Notice we have 2 decimal places for all burette readings. Your burette does not have to start at 0. My next measurement is going to probably start wherever I left off, depending on how much I have. I need to make sure I've got enough volume left, right? Or I have to do some adding together that isn't necessary if I pay attention, right? So let's pretend like I measure this as my final volume. And then my next measurement, I only spent 21.25 milliliters for that titration, so I don't need to refill it. For my next titration, let's say I go and titrate it again, but this time it's 42.7. I don't want to confuse you. We can have different numbers than a 5 at the end. We'll do 0.72. Again, I'm making up these numbers, okay? But they're not unreasonable for the experiment you're doing. When you go home, what you do need to do in the lab, and it's handy to bring your calculator, is calculate the volume of NaOH that you actually put in. Okay. You should organize your data tables before lab, so like this should actually go up above your burette readings. But here, obviously, the volume that we delivered was 21.25 minus 0, not divided by, minus 0. So we put in 21.25 milliliters of NaOH. Over here, we would have to subtract them, right? So 42.72 minus 21.25. So that's final minus initial. And that will give us how much base we actually put in during that titration. And so we got 21.47. These two are within 1/2 of a milliliter of each other. So that's fantastic. This is a great result for this level of chemistry. You would do a third run, and hopefully it's near these two, and then you can move on to the next part of the experiment. Okay, so you may need a calculator in lab just to make sure that you're within 1/2 milliliter of NaOH delivered. Because if you're not, then you have to do it a 4th time. Okay, so when you get home, though, this is the only calculation you really need to do in the lab. When you get home, here's how we're going to approach the problem. We know that there's this many grams of oxalic acid dihydrate. On the pre-lab, you should have already computed the molar mass of this, because you have to figure out your range. Make sure that you include the water as part of your weight. Whatever that number is, you're going to use it. I'm just going to abbreviate. The molecular weight goes on the bottom, and then we'll cancel the grams. That'll get us to moles of oxalic. Once you dissolve the oxalic acid in the water, the water molecules stuck to it dissociate. They go about their own business. So once you've computed this, you no longer need to include the hydrate anymore. I don't want to give away the answers to the pre-lab, so I will just leave this as a theoretical value. Okay. Once you have the moles of oxalic acid, you will look in the procedure. Board's PowerPoint wasn't cooperating. Anyway, so at the end of that last calculation, you'll have moles of oxalic acid, and you need to divide by liters. So this is the liters that you dissolved all of the oxalic up into, which is 250 milliliters. So convert that into liters, plug it into here, and that will give you the molarity of your oxalic acid. Once you have that, then you're going to go into the procedure and you're going to look and see what volume is pipetted into each reaction flask. The answer is in question 3, or procedural step 3, not question 3. All right, so then what we're going to do is we're going to take our molarity of oxalic acid, whatever number that ends up being, and you're going to multiply by that volume. This is per titration, right? So we're doing this one step at a time for each titration. We're not going to take this entire 250 ml flask and react it all at one time. That would take way too much base. So this is just for one titration. So our molarity times milliliters, of course, that doesn't cancel, so we'll still have to convert here. Unless you're comfortable with millimoles, I am. So if you want to use it that way, that's fine by me. If you're not comfortable with it, don't do it. All right, and so this will mean our moles per liter, our liters will cancel, our milliliters will cancel. We will get the number of moles of oxalic acid per titration. This will be a consistent number, so you only really have to do this calculation one time. Okay, for all your titrations in the standardization of the base, we'll be using the same number of moles of oxalic. So then the next part will differ. All right, I'm just going to make up a number of moles to illustrate how to do this part. It will be different from yours because I'm making it up. You will have lots of precision though. So I'm going to keep all my significant figures. Let's say I react that many moles of oxalic acid. Okay, so what I will do is using 4 zeros. Using that as the basis, I will convert it so that we can compare the sodium hydroxide. In order to do that, of course, we need a balanced chemical reaction. The answer to this will also be in your pre-lab, right? Remember that a neutralization reaction always produces water. And remember how we talked about the number of water should be reflected over here. And it will produce a salt. This is just like every other double displacement. This reaction is not balanced because I need to have 2 sodium hydroxide in order to make 2 sodiums and 2 water. All right. So we'll pop 2 NaOH on the top because that's what I'm trying to get into. And we have 1 H2C2O4. That's 1 mole. I'll fix that up there. All right, so there's our balanced reaction. I'm going to use it to convert moles. And we find out that we get double the number of moles of NaOH that we had for our oxalic acid because it's a 2-to-1 reaction. So the next step will be, well, actually this step is the same for all your reactions as well. So you only have to do all of this one time. The part that you need to do for each titration will be to take this number of moles and divide it by the total volume of NaOH that you put in for that reaction. So we just calculated that a second ago. It was 21.25 milliliters. That does need to be converted into liters, so you can either do that as a separate step or as part of this, however you want to handle that. That answer will be your molarity. So in this example calculation, I calculated 9.41176. There's more. I'm going to stop there. And then I go back and I look and I got 1, 2, 3, 4, 5 sig figs from my moles, and I have 4 from my volume, so we'll keep just 4. So I got to round at this position. So it'll be 9.412 molarity NaOH. Now, obviously, this is way higher than what you're actually going to get. Remember, I made up this number of moles. Yours will be different. But the method is the same. Okay? So, you know what the answers should be roughly because you calculate it. It's in the procedure. If you read carefully, the pre-lab tells you the the approximate concentration of the oxalic acid, and the procedure tells you the approximate concentration of the NaOH. So that's not a mystery. You know more or less what you're shooting for. The part that you're solving is the sig figs, right? So instead of 1 or 2 significant digits, you're going to end up with 4. Okay, so pay attention to that. But the answer should not be a total surprise to you. Once you've standardized your NaOH, then you are ready to use this in a similar way to what we just did to calculate the amount of your unknown acid. So this process here is called standardizing the NaOH. The next step is to take your unknown acid, right? And so this will be a separate titration. You're still using the initial amount of NaOH in the lab and the final. These are your burette readings again. And so the difference is when you do your unknown acid, you're only going to measure 10.00 milliliters. This is with a pipette. And your unknown acid could be one of 2. It might be sulfuric. You need to write this down when you're in the lab. Or it might be acetic. The bottle is labeled. Write it down. You also need to write down your unknown number. Okay? But same strategy. You're going to be recording the initial volume of NaOH, the final volume of NaOH, and then subtracting to get how much NaOH you actually have put in. You need to get 3 titrations within a half a milliliter of each other. Okay? So when you're actually in the lab, if it takes longer than 2 hours to standardize your sodium hydroxide, so that's the first 3 titrations you're supposed to get, I would encourage you to go on anyway. Check with your lab professor at that point because you may need help with your technique. But generally, it's going to take you at least an hour to do your 3 titrations of your unknown. And if you don't do those, you'll have to come back to lab to finish them later. The people who are prepared and have watched the skills videos and sort of thought about what they did in the beginning of the semester with the pipettes and the burettes, we'll get through this with no problem. But for those of you who don't remember that or struggled or missed that experiment, seek help from your lab professor if you're having difficulty getting repeatable measurements. One quick aside, what do I mean by having difficulty? What you're trying to get is 3 titrations that are pale pink like this. You have to put it against a white surface to see it, but they stay pale pink for 30 seconds. And that counts as the end of your titration. We call that the endpoint. If you're titrating and getting a dark, dark pink, that's way too much base added. Okay, so you want to go slow when you get near your endpoint. After you do your first titration, you know roughly what volume that is, and so you can slow down around that volume and get better and better titrations as you go along. But you want 3 pale pink that agree within a half a milliliter of each other. So in your data table, it's a good idea to also note the color at the end point. So it might say pale pink, or it might say dark pink or fuchsia. Hopefully not, but having that observation can also help. I think we will do another video of titration calculations again. This is a good introduction. Hopefully you're prepared for the lab. After the lab, there will be additional calculations we can work on together.